Bismillahirrahmanirrahim. Assalamu alaikum. My name is Syed Kashif and I am doing bachelor's in chemistry from University of Management and Technology. So today I'm here to present the topic of the presentation, which is based on nuclear magnetic resonance spectroscopy. So I tried to cover all the aspects of this spectroscopy, so we will see in detail all the aspects of the NMR. So let's see what comes next. So these are the contents of the presentation. First we will see about the introduction to NMR, what it is actually, what are the basic principles behind it, what are the quantum descriptions of the NMR, classical description of NMR, types of NMR spectra, chemical shifts, NMR spectrometers, instrumentation, NMR spectroscopy principles, and NMR working and software. So these are the main highlights of this presentation. So let's move on. So introduction to NMR. The nuclear magnetic resonance spectroscopy, it is the study of the molecules by recording the interaction of the radio frequency electromagnetic radiations with the nuclei of the molecules which are placed in a strong magnetic field. So it is basically the interaction of the nuclei of the molecules with the strong magnetic field by interaction of the radio frequency electromagnetic radiations. So the Zeeman first observed the strange behavior of certain nuclei when subjected to a strong magnetic field at the end of the 19th century. But the practical use of so-called Zeeman effect was only made in the 1950s when the NMR spectrometers became commercially available. It is a research technique that exploits the magnetic properties of certain atomic nuclei. The NMR spectroscopy determines the physical and the chemical properties of atoms or molecules. It relies on the phenomenon of the nuclear magnetic resonance and provides in detailed information about the structure, dynamics, reaction state, and the chemical environment of molecules. So it was the introduction to NMR. Let's see what comes next. So the basics of NMR spectroscopy. The nuclear magnetic resonance was first detected experimentally at the end of 1945, nearly concurrently with the work groups Felix Bloch, Stanford University, and the Edward Purcell, Harvard University. The first NMR spectrum was first published in the same issue of the Physical Review in the January 1946. Bloch and Purcell were jointly awarded the 1952 Nobel Prize in Physics for their research of nuclear magnetic resonance spectroscopy. The nuclear magnetic resonance spectroscopy, it is a crucial analytical tool for the organic chemists. The research in the organic lab, it has been significantly improved with the aid of the NMR. So it was the basics of the NMR. Not only can it provide the information on the structure of the molecule, it can also determine the content and purity of the sample. Proton managed NMR, it is one of the most widely used NMR methods by the organic chemists. The protons present in the molecule will behave differently depending on the surrounding chemical environment, making it possible to elucidate their structure. Okay. So the next topic will be the quantum description of the NMR. To account for the properties of certain nuclei, we must assume that they rotate about an axis, thus they have a property of spin. Nuclei with a spin have angular momentum p. Furthermore, the maximum observable component of this angular momentum is quantized and must be an integral or half integral multiple of h over 2p, where h is the Planck's constant. The maximum number of spin components or values for p for a particular nucleus is its spin quantum number. The nucleus will then have 2i plus 1 discrete states. The component of angular momentum for these states in any chosen direction will have values of I minus 1, I minus 2 or 2i. In the absence of an external field, the various states have identical energies. The four nuclei that have been of the greatest use to organic chemists and biochemists are hydrogen, 13 carbon, 19 fluorine and 31 phosphorus, and they are the only four we will discuss. The spin quantum number for these nuclei is 1 by 2. Thus the each nucleus has two states corresponding to I is equal to 1 plus I is equal to plus 1 by 2 and I is equal to minus 1 by 2. Heavier nuclei have spin numbers that range from 0, which implies that they have no net spin component to at least 9 by 2. A spinning charged nucleus creates a magnetic field analogous to the field produced when the electricity flows through a coil of wire. The resulting magnetic moment M is oriented along the axis of spin and it is proportional to the angular momentum. Thus, U is equal to gamma p, where the proportionality constant gamma it is the magnetogyric or the gyromagnetic ratio, which has a different value for each type of nucleus. The relationship between the nuclear spin and the magnetic moment leads to a set of observable magnetic quantum states M, given by M is equal to I minus 1, I minus 2 or minus I. Thus the nuclei that we will consider have two magnetic quantum numbers, M is equal to plus 1 by 2 and M is equal to minus 1 by 2. Note that the rules for the determining nuclear quantum numbers are similar to those for the electronic quantum numbers. Okay. So we will see now the energy levels in a magnetic field. When a nucleus with a spin quantum number of 1 by 2 is brought into an external magnetic field BO, its magnetic moment becomes oriented in one of the two directions with respect to the field, depending on its magnetic quantum state. The potential energy E of a nucleus in these two orientations or quantum states is given by this formula. The energy for the lower states M is equal to plus 1 over 2 states is given by E plus 1 over 2 is equal to gamma H Planck, which is the Planck constant 4 pi BO magnetic field. For the M is equal to minus 1 by 2 state, the energy is E minus 1 by 2, it is equal to YH 4 pi BO. Thus the difference in energy dE between the two states is given by subtracting the formula, so we will get the desired answer. As in other types of spectroscopy, transitions between the energy states can be brought about by absorption or emission of electromagnetic radiation of a frequency NO that corresponds in energy to delta E. Thus, by substituting the Planck relationship into this equation, we obtain the frequency of the radiation required to bring about the transition. It is given by the formula. So this is the figure which describes the magnetic moments and energy level for a nucleus with a spin quantum number of 1 by 2. So each characteristic is described very beautifully. So moving towards the next slide. Classical description of NMR. Okay, the relaxation processes in NMR. When a nucleus is exposed to radiation of a suitable frequency, absorption occurs because of the slightest excess of lower energy state nuclei present in the strong magnetic field. This excess is small, so there is always danger that the absorption process will equalize the number of nuclei in the two states and cause the absorption signal to decrease and to approach zero. When this occurs, the spin system is said to be saturated. To avoid saturation, the rate of relaxation of excited nuclei to their lower energy state must be as greater or greater than the rate at which they absorb the RF energy. One apparent relaxation path is the emission of radiation of a frequency corresponding to the energy difference between the states as occurs in fluorescence. Radiation theory, however, shows that the probability of spontaneous re-emission of photons varies as the cube of the frequency, and that at radio frequencies this process does not occur at a significant extent. To reduce the saturation and produce a readily detectable absorption signal, relaxation should occur as rapidly as possible. That is, the lifetime of the excited state should be small. A second factor, the inverse relationship between the lifetime of an excited state and the width of its absorption line negates the advantage of very short lifetimes. Thus, when relaxation rates are high or the lifetimes low, line broadening prevents the high resolution measurements. These two opposing factors cause the optimal half-life for an excited species to range from about 0.1 to 10 seconds. Okay. So there are two types of relaxation processes in NMR. The first one is spin lattice or longitudinal relaxation, or spin or transverse relaxation. Spin lattice relaxation is the relaxation time T1 quantifies the rate of transfer of energy from the nuclear spin system to the neighboring molecule, the lattice. This is relaxation in the z direction and leads to the restoration of Boltzmann equilibrium. Spin relaxation exists because the NMR spectrometers detect signals only when the magnetic movements of entire populations of nuclei are aligned and moving in synchrony. So these are the diagrams shown two nuclear relaxation processes. Longitudinal spin lattice relaxation takes place in the xy plane, transverse spin relaxation in the xy plane. So it is described. So next is the Fourier transform nuclear magnetic resonance. Fourier transform nuclear magnetic resonance is an analytical technique used to analyze the structure of the molecule ranging from a small organic molecule or a metabolite to a mid-sized peptide or a natural synthetic product based on the magnetic property of certain nuclei. An NMR experiment consists of these three steps. Place the sample in a static magnetic field, excite the nuclei in the sample with a radio frequency pulse. Measure the frequency of the signals emitted by the sample. From the emitted frequencies, the information about the bonding and the arrangement of the atoms in the sample is recorded as free induction decay or FID. By using the mathematical calculation Fourier transform, the FID data is converted to spectra. Pulsed excitation, the figure will come. It shows the position of the net magnetic movement at the instant of the pulse of the RF radiation traveling along the x-axis strikes the sample. The magnetic field of the incident electromagnetic radiation is given the symbol B1. In the rotating frame, B1 and the sample magnetization vector M are both static, one along the x-axis and the other at right angles to it. Basic physics tells us that that with each pulse, M experiences a torque that tips it off the z-axis. So this is described as the pulse excitation behavior of magnetic movements of nuclei in a rotating field of reference. 90-degree pulse experiment. Magnetic vectors of excess lower energy nuclei just before the pulse. BCD rotation of the sample magnetization vector M during the lifetime of the pulse, relaxation after the termination of the pulse. As shown in the figure and the D, this torque rotates the sample magnetic movement M around the x-axis in the YZ plane. The extent of rotation depends on the length of the pulse at it is given by alpha is equal to YB1 time period pulse, where alpha is the angle of the rotation in radians. For many Fourier transform experiments, a pulse length is chosen so that alpha is 90 degree or pi by 2 p by 2 radiation as shown in the figure 19.6d. Typically, the time required to achieve this angle is 1 to 10 microseconds. Once the pulse is terminated, nuclei begin to relax and return to their equilibrium position as shown in the figure. As discussed in the previous section, relaxation takes place by two independent mechanisms, spin lattice and spin interactions. After several seconds, as a result of these interactions, the nuclei return to their original state as depicted in the figure 19.6a. When a nucleus returns to its equilibrium state after being tipped by a pulse of RF radiation, as shown in the figure, the magnetic movement my along the y-axis decreases and the magnetic movement mz along the z-axis increases. Free induction decay. Let us turn again to the figure 19.60 and consider the situation when the signal B1 goes to 0 at the end of the pulse. Now, however, it is useful to picture what is happening in the static frame of reference rather than the rotating frame. If the coordinates are fixed, the magnetic movement M must now rotate the clockwise around the z-axis at the Larmor frequency. This motion gives rise to an RF signal that can be detected by a coil along the x-axis. As mentioned earlier, it can be detected with the same coil used to produce the original pulse. As relaxation proceeds, this signal decreases exponentially and approaches zero as the magnetic vector approaches the z-axis. This figure illustrates the FID that the signal is produced by the 413C nuclei in dioxane which behave identically in the magnetic field. The FID in figure 19 0.88, it is an exponential curve that approaches zero after a few tenths of a second. The apparent noise superimposed on the decay pattern is that it is an experimental artifact caused by spinning side bands, and for the purposes of our discussion can be disregarded. Figure 19.8b, it is the Fourier transform of the curve in figure 19.8a, which shows on the left of the single 13C absorption peak for dioxane. This effect is shown in the figure 19.9, in which the difference in the two frequencies is 50 Hz. So this is the figure that is trying to show that 13 CFID signal for dioxane when pulse frequency differs from the Larmor frequency by 50 Hz. The B segment shows the Fourier transform of A. So this was the description of the previous material. When magnetically different nuclei are present, the FID develops a distinct beat pattern such as that in figure 19.10a, which is a spectrum for the 13C nuclei in cyclohexane. This compound contains the three pairs of magnetically different carbon atoms, the pair of olefinic carbons, the pair of aliphatic carbons adjacent to the olefinic pair, the pair and the pair directly opposite to the olefinic group. The lines in figure 19.10b that differ by 62 Hz arise from the two pairs of aliphatic carbon atoms. The pair of olefinic carbons is responsible for the single resonance on the left. With compounds having several absorption lines, the FID becomes very complex. So we are now going to discuss the types of NMR spectra. There are several types of NMR spectra depending on the kind of instrument used, the type of nucleus involved, the physical state of sample, the environment of the analyzed nucleus, and the purpose of the data collection. Most NMR spectra can, however, be characterized as either the wide line or high resolution. Wide line spectra. Wide line spectra are those in which the bandwidth of the sources of the lines is large enough that the fine structure due to the chemical environment is obscured. Figure 19.11, it is a wide line spectrum for a mixture of several isotopes. A single resonance is associated with each species. Wide line spectra, they are used for the quantitative determination of isotopes and for the studies of the physical environment of the absorbing species. Wide line spectra are usually obtained at relatively low magnetic field strength. So this is the wide line spectra. It shows a low resolution NMR spectrum of water in a glass container. Frequency is equal to 5 MHz. High resolution spectra. Most NMR spectra are high resolution and are collected by instruments capable of differentiating between very small frequency differences of 0.01 ppm or less. For a given isotope, such spectra usually exhibit several resonances that result from differences in their chemical environment. Figure 19.12 illustrates the two spectra of different resolution for the protons in ethanol. In the upper spectrum, three peaks arrive from absorption by CH3 and CH2 and OH protons. As shown in the higher resolution spectrum of figure 19.12b, two of the three peaks can be resolved into additional resonances. So these are the NMR spectra of ethanol at a frequency of 60 MHz resolution at 1 divided by 10 to the power 6 and B 10 raised to power 7. Theory of chemical shift. So we will discuss it. Chemical shifts arise from the secondary magnetic fields produced by the circulation of electrons in the molecule. These so-called local diamagnetic currents are induced by the fixed magnetic field and results in secondary fields that may either decrease or enhance the field to which a given proton responds. The effects are complex and we consider only the major aspects of the phenomenon here. More complete treatments can be found in several reference works. Under the influence of the magnetic field, electrons bonding the proton tend to precess around the nucleus in a plane perpendicular to the magnetic field. A consequence of this motion is the development of a secondary field which opposes the primary field. Analogous to what happens when electrons pass through a wire loop, the nucleus then experiences a resultant field that is smaller, so the nucleus is said to be shielded from the full effect of the primary field. As a consequence, the external field must be increased to cause the nuclear resonance. So this is the diamagnetic shielding of a nucleus, circulating electrons, nucleus, and the secondary field, applied field, which is the magnetic field. The shielding experienced by a given nucleus is directly related to the electron density surrounding it. Thus, in the absence of the other influences, shielding would be expected to decrease with increasing electronegativity of the adjacent groups. This effect is illustrated by the d values for the protons in the methyl halide CH3X, which lie in the order of these as shown below. In this example, the least electronegative halogen, thus the electrons of the iodine provides the smallest shielding effect. Effect of magnetic anisotropy. The effects of multiple bondings on the chemical shift can be explained by taking into account the anisotropic magnetic properties of these compounds. For example, the magnetic susceptibilities of crystalline aromatic compounds have been found to differ appreciably from one another depending on the orientation of the ring with respect to the applied field. This anisotropy can be understood from the model shown in the figure 19.15. In this model, the plane of the ring is perpendicular to the p electrons around the ring to create a so-called ring current. So this is the induced field sigma BO ring current and the applied magnetic field. The shielding of aromatic protons brought about the ring current. A ring current is similar to a current in a wire loop, that is, a secondary field is induced that acts in opposition to the applied field. This induced field, however, exerts a magnetic effect on the protons attached to the ring in the direction of the field as shown in the figure. Thus, the aromatic protons require a lower external field to bring them into resonance. This effect is either absent or self-cancelling in other orientations of the ring. An analogous model operates for the ethylenic or carbonyl double bonds. In such cases, we may imagine p electrons circulating in a plane along with the bonding axis. When the molecule is oriented with the field as presented in the figure 19.16a, again the secondary field produced acts on the proton to reinforce the applied field. Thus, de-shielding shifts the peak to the larger values of D with an aldehyde. This effect combines with the de-shielding brought about by the electronegative nature of the carbonyl group and a very large value of the D results. So these are the de-shielding effects of the ethylene and shielding of acetylene brought about by the electronic currents. Effects of chemical exchange on the spectra. We now turn again to the NMR spectrum of an ethanol and consider why the OH proton resonance appears as a singlet rather than a triplet. The methylene protons and the OH protons are separated by only 3 bonds, so coupling should increase the multiplicity of both OH and the methylene bands. As shown in the figure, we actually observe the expected multiplicity in the NMR spectrum of a highly purified sample of the alcohol. Examine the triplet OH peaks and the 8 methylene peaks in the spectrum. So this is the spectrum which we are talking about, NMR spectra of ethanol we also saw it previously. The exchange of OH protons among the alcohol molecules is known to be catalyzed by both acids and bases, as well as by the impurities that commonly occur in ethanol. It is thus plausible to associate the decoupling observed in the presence of these catalysts to an exchange processes. If the exchange is rapid, each OH group will have several protons associated with it during any brief period. Within this interval, all of the OH protons will experience the effects of the 3 spin arrangements of methylene protons. Thus, magnetic effects on the alcoholic protons are averaged and a single sharp resonance is observed. Spin decoupling always occurs when the exchange frequency is greater than the separation frequency between the interacting components. So we will now discuss the NMR spectrometers. Instrument manufacturers market 2 general types of NMR spectrometers: wide line spectrometers and high resolution spectrometers. Wide line instruments have magnets with a strength of a few tenths of a Tesla and are considerably simpler and less expensive than our high resolution instruments. High resolution instruments are equipped with magnets with strengths that range from 1.4 to 23.5 Tesla, which correspond to proton frequencies of 60 to 1000 megahertz, 1 gigahertz. So, what are the components of Fourier transfer spectrometers? It is a simplified block diagram showing the instrument components of a typical FT NMR. The central component of the instrument is a highly stable magnet in which the sample is placed. The sample is surrounded by a transmitter receiver coil. RF radiation is produced by a crystal control frequency synthesizer having an output carrier frequency of NC. This signal passes into a pulse switch and power amplifier, which creates an intense and reproducible pulse of RF current in the transmitter coil. The resulting RF radiation impinges on the sample contained inside the coil. This length, amplitude, shape, and phase of the pulse are selected by the operator, entered into the console, and controlled by the computer. In the figure, a 5 microsecond pulse is shown. The resulting FID signal is picked up by the same coil, which now serves as a receiver. The signal is then amplified and transmitted to a phase-sensitive detector. The detector circuit reproduces the difference between the nuclear signals NN and the crystal oscillator output NC, which leads to the low-frequency time-domain signal shown on the right of the figure. This signal is digitized and collected in the memory of the computer for analysis by a Fourier transform program and other data analysis software. The output from this program is plotted on a display device giving a frequency domain spectrum. So this is the overall block diagram of an FT NMR spectrometer. So this is the pictorial representation of the NMR FT NMR. Fourier transform computer, pulse switch, frequency synthesizer, RF amplifier, phase sensitive detector, RF amplifier. So these are the diagrams. Instrumentation of NMR magnet. The heart of all NMR instruments is the magnet. The sensitivity and the resolution of the spectrometers are both critically dependent on the strength and quality of their magnets. Because both sensitivity and resolution increases with the increase in field strength, it is advantageous to operate at the highest possible field strength. In addition, the field must be highly homogeneous and reproducible. These requirements ensure that the magnet is by far the most expensive component of an NMR spectrometer. Spectrometer magnets of the three types have been used in the NMR spectrometers: permanent magnets, conventional electromagnets, and the superconducting solenoids. Conventional electromagnets are the seldom incorporated into NMR instruments. Permanent magnets with the field strength of 0.7, 1.4, and 2.1 Tesla have been used in the commercial CW instruments. Corresponding oscillator frequencies for proton studies are 30, 60, and 90 MHz. Permanent magnets are highly temperature sensitive and require extensive thermostating and shielding as a consequence. Because of field drift problems, permanent magnets are not ideal for extended periods of data accumulation, such as are often used in Fourier transform experiments. Superconducting magnets. They are used in most modern high resolution instruments. These magnets attain fields as large as 23.5 Tesla, corresponding to a proton frequency of 1 GHz. To superconduct, the solenoid wound from the superconducting niobium tin or niobium titanium wire is bathed in the liquid helium at a temperature of 4 Kelvin. The helium dagger flask is held in an outer liquid region dagger. Most superconducting magnetic systems must be filled with the liquid nitrogen about once a week and with liquid helium every few months. The advantages of superconducting solenoids, in addition to their high field strength, are their high stability, low operating cost, simplicity, and small size compared with an electromagnet. Locking the magnetic field. To offset the effect of field fluctuations, a field frequency lock system is used in commercial NMR systems. In these systems, a reference nucleus is continuously irradiated and monitored at a frequency corresponding to its resonance maximum at the rated field strength of the magnet. Thus, the drift correction for the reference signal is applicable to the signal of for all the nuclei in the sample area. In modern spectrometers, the reference signal is provided by the deuterium in the solvent and a second transmitter coil turned to the frequency of deuterium monitors the reference. Most modern superconducting magnets are sufficiently stable that spectra can be obtained in an unlocked mode for a period of 1 to 20 minutes. Shimming Shim coils are the pairs of wire loops through which carefully controlled currents are passed, producing small magnetic fields that compensate for inhomogeneities in the primary magnetic field. In contemporary instruments, the shim controls are under computer control with several algorithms available for optimizing the field homogeneity. Ordinarily, shimming must be carried out. What is sample spinning? The effects of field inhomogeneities are also contracted by spinning and spinning the sample along its longitudinal axis. The spinning is accomplished by means of a small plastic turbine that slips over the sample tube. A stream of air drives the turbine at a rate of 20 to 50 revolutions per second. If this frequency is much greater than the frequency spread caused by magnetic inhomogeneities, the nuclei experience an averaged environment that causes apparent frequency dispersion to collapse towards the zero. Sample probe. A key component of an NMR spectrometer is the sample probe, which serves multiple functions. It holds the sample in a fixed position in the magnetic field, contains an air turbine to spin the sample, and the houses and the coil or the coil that permits the excitation and detection of the NMR signal. Finally, most probes have variable temperatures capability. The usual NMR sample cell consists of 5 mm outside diameter glass tube containing 500 to 650 microliters of the liquid. Transmitter receiver coil. The adjustable probes in the modern NMR spectrometers contain transmitter and receiver coils. The receiver coils are arranged according to the experiment purpose. For observing the protons, the probe usually has an inner coil for 1s detection and an outer coil called the X nucleus coil for detecting the nuclei such as 13 carbon or 15 nitrogen. The inner coil is generally the closest to the sample to maximize the sensitivity. For experiments to detect the nuclei other than the protons, the X nucleus coil is replaced on the inside and the 1H coil on the outside. Usually, proton spectra have good signal to noise ratios that probe tuning is not extremely critical. The pulse generator. RF generators and the frequency synthesizers produce a signal of an essentially a single frequency to generate the Fourier transform spectra. However, the sample must be irradiated with a range of frequencies sufficiently great to excite the nuclei with the different resonance frequencies. Fortunately, a sufficiently short pulse of radiation it provides a relatively broad band of frequencies centered on the frequency of the oscillator. The frequency range of this band is about 1 by 4 times hertz, where it is the length in seconds of each pulse. Thus, a 1 microsecond pulse from a 100 MHz oscillator produces a frequency range of 100 MHz to 6 to 125 kHz. Conversely, the Fourier analysis of a square waveform reveals that it consists of a broad range of frequency components. The narrower the square wave, the broader the range of the component frequencies. Thus, a narrow pulse generated by rapidly switching an RF oscillator consists of a band of frequencies capable of exciting all nuclei whose resonances occur in the vicinity of the frequency of the oscillator. The receiver system. Voltage is generated by the current in the director coil or in the nanovolt to microvolt range and thus must be amplified to a range of about 0 to 10 volt before the signal can be further processed and digitized. The first stage of amplification generally takes place in a preamplifier which is mounted in the probe so that it is as close to the receiver coil as possible to minimize the effects of noise from the other parts of the instrument. 5 lakh 50 lakh to 50 lakh 5000 hertz. To digitize such high frequency signal and extract the small differences attributed to the sample in the digital domain is not practical. Therefore, the carrier frequency Nc is subtracted electronically from the analyte signal frequency Nn in the analog domain. So this process is identical to the separation of audio signals from an RF carrier signal in the home radios, the detector and the data processing system. In the detector system shown in the figure 19.21, the frequency radio signal is first converted to an audio frequency signal, which is much easier to digitize. The analyte signal differs in the frequency from that of the carrier by a few parts per million. For example, the chemical shifts in a proton spectrum typically encompasses a range of 10 ppm. Thus, the proton NMR data generated by 500 MHz spectrometer would lie in the frequency range of 50 lakhs to 50 lakhs 5000 Hz. To digitize such frequency signals and extract the small differences attributed to the sample in the digital domain is not practical. Therefore, the carrier frequency NC in subtracted electronically from the analyte signal frequency Nn in the analog domain. So, what is sampling the audio signal? The sinusoidal audio signal is obtained after subtracting the carrier frequency, is then digitized by sampling the signal voltage, periodically converting it to a digital form with an analog to digital converter. To accurately represent a sine or cosine wave digitally, it is necessary, according to the Nyquist sampling theorem, see section 5c, to sample the signal at least twice during each cycle. If sampling is done at a frequency that is less than twice the signal frequency, folding or aliasing of that signal occurs. The effect of folding is illustrated in the figure, which shows us as the dashed curve a 1600 Hz curve cosine signals that is being sampled at a rate of 2000 data per second. This sampling rate is less than the Nyquist frequency, which is 2 to 3 1600 Hz. This effect of this inadequate sampling rate is demonstrated by the solid curve in figure 19.22a, which is a 400 Hz cosine wave. Thus, as shown in the figure, the line at 1600 Hz is absent and a folded line appears at 400 Hz. So this is the description folding of a spectral line brought about by sampling at a frequency that is less than the Nyquist frequency of 3200 Hz. So this is the description. Signal integration. The areas of proton NMR signals are almost always directly proportional to the number of protons involved. Hence, the modern NMR spectrometers provide not only the NMR signal itself, but for 1s spectra, is the integral of the signal. For 13 carbon spectra, the signals are not in general not proportional to the number of nuclei present. Usually the integral data appear as step functions superimposed on the NMR spectrum. So this is the description, absorption and integral curve for a dilute ethyl benzene solution. Sample handling. Until recently, high resolution NMR studies have been restricted to samples that could be converted to a non-viscous liquid state. Most often a 2% to 15% solution of the sample is used, although pure liquid samples can also be examined if their viscosities are sufficiently high. Solvents must have no resonances of their own in the spectral region of interest. Usually, the NMR solvents are deuterated to provide the field frequency log signal. The most commonly used solvent for organic compound is deuterated chloroform CdCl3. Polar compounds are often not sufficiently soluble in CdCl3 to obtain a good spectra. For these types of compounds CD3OD, acetone D6 and DMSOD6 are often used. For highly polar and organic compounds, ionic compound D2O can be used along with a water suppression method to remove the intense HOD solvent. High quality NMR tubes are necessary with the modern high field spectrometers. If tubes have been previously used, they must be carefully cleaned and thoroughly dried prior to use. Sample tube cleaners are available commercially for this purpose. Cleaning solutions such as chromic acid, sulfuric acid should never be used because paramagnetic chromium ions can adsorb to the walls and broaden the proton NMR spectra. So, what is the NMR spectroscopy principle? Many nuclei have spin and all nuclei are electrically charged according to the NMR principle. An energy transfer from the base energy to a higher energy level is achievable when an external magnetic field is supplied. All the nuclei are electrically charged and many have spin. Transfer of energy is possible from the base energy to the higher energy levels when an external magnetic field is applied. The transfer of energy occurs at a wavelength that coincides with the radio frequency. Also, energy is emitted at the same frequency when the spin comes back to its base level. Therefore, by measuring the signal which matches this transfer, the processing of the NMR spectrum for the concerned nucleus is yield. So this is the spectrum. This is the depiction, the case of the spin minus 1 by 2. The nuclei are electronically charged and many have spin that causes them to behave like a magnet. Energy gap corresponds to radio frequency. So talking about the less energy, a nucleus with spin at lower energy generates a magnetic field in the direction of external magnetic field. A nucleus with spin at higher energy generates a magnetic field in the opposite direction to the external magnetic field. So talking about the NMR spectroscopy working, place the sample in a magnetic field. Excite the nuclear sample into nuclear magnetic resonance with the help of radio waves to produce NMR signals. These NMR signals are detected with sensitive radio receivers. The resonance frequency of an atom in a molecule is changed by the intramolecular magnetic field surrounded by it. This gives the details of a molecule's individual functional groups and its electronic structure. Nuclear magnetic resonance spectroscopy is a conclusive method of identifying the monomolecular organic compounds. This method provides the details of the reaction state, structure, chemical environment, and dynamics of a molecule. So this is actually recalling the NMR spectroscopy instrumentation. So in the last we will talk about the applications of NMR and the software used. The advanced analytical technique allows researchers to study the unique chemical, physical, and biological characteristics of a molecule with a method used across a wide range of fields and professions. Read on to find out more about the different uses of the NMR spectroscopy. Chemistry laboratories. Chemists rely on nuclear magnetic resonance spectroscopy as a tool to chart the complex molecular structures of the matter. The technique sees samples placed in a specialized NMR spectrometer where it is exposed to a strong magnetic field. The gravitational pull generated by the field excites the nuclei of some atoms and creates resonant frequencies. These resonant frequencies are then tracked, measured, and used to generate the useful data. Food quality control and research. Before hitting the consumer market, foods undergo strict quality control and research studies. NMR spectroscopy is widely used across the industry to map the protein structures, profile amino acids, identify the carotenoids, and quantify the metabolites. Most people are familiar with the magnetic resonance imaging scans, which uses powerful magnetic fields and radio waves to reveal the detailed images of the internal organs. Data is generated based on the rates of absorption and energy emission recorded in the radio frequency RF range. The medical imaging technique is founded in NMR spectroscopy and uses the same basic principles. Identifying the human disorders. When used alongside the metabolic mix, that NMR spectroscopy is an individual tool for identifying the human disorders. The cellular metabolism contains important biomarkers used to diagnose a wide range of conditions, including the tuberculosis, pneumonia, and malaria. NMR spectroscopy allows the researchers to identify these telltale biomarkers and treat patients accordingly. The technique can also be used to investigate the Parkinson's disease as well as the cardiovascular diseases and a range of neuropsychiatric disorders such as bipolar, major depression, and autism spectrum disorders. Drug discovery and development, from trailing new cancer therapies to perfecting the nutritional supplements. NMR spectroscopy is a mainstay in the drug discovery and development. Dr. Robin J. Black, a representative from UK-based manufacturing and research company Oxford Instruments, offers more information on the latest NMR spectroscopy techniques and instruments in X nuclei NMR spectroscopy. So if we talk about the NMR Spectroscopy Spectrometer Suppliers, Newmark Corporation, Magnetic Inc., International Scientific Gear, Wavewide Corporation, Seago Nanotools, Oxford Instruments, COSA Centaur Corporation, MRI Global, CBRNE, Tech Index, Bruker Corporation. So in the last we will talk about the software which is used in the NMR. For analysis of NMR data from the small molecules, users are primarily using Topspin and Mastrinova. Topspin is the software used for the acquisition, but it is also used for processing and data analysis. Mastrinova is only used for processing and data analysis. So at this point it concludes all of my presentation topics and the contents. I hope you will enjoy the presentation. Till next time, Allah Hafiz.